Okay, here we have homework 3, part C. The question is, for liquid water evaporating from a pool in a tube with stagnant vapor phase, where a stream of dry nitrogen flows to remove all moisture at the top, explain the driving force for evaporation, diffusion of water and nitrogen. Write down the pertinent equations and explain how the gradient in nitrogen concentration leads to diffusion towards the pool, but results in no net nitrogen flux. So we're just going to focus on part 1 for now. So, we can start with, we're going to have our Fick's law we're going to use to go over just about everything in this question. So what we have Fick's law is we're going to have our J1, which is our molar flux, is equal to our diffusion coefficient times our dx1 over our dz, which is our gradient, and then we're going to have that multiplied by negative c, which is our concentration. So this concentration can be written as, let's just write this out. So concentration can be written as moles per liter, or N over V, which we can relate using one of our favorite laws, which is PV equals nRT. Or, well, in this case, we need to have it rewritten as NV over PRT. So it looks good. Now what we need to do is just balance our concentrations. So we're going to have, in our whole container here, we only have nitrogen and water. So we're going to have our nitrogen plus our water is going to be equal to our C total, our total concentration. We can rewrite that simply as, so our two C's put together. So P over RT of our nitrogen plus our P over RT of our water is equal to C total. So that looks good as a good start. So I'll be back and we'll kind of explain some of these concepts better. Okay, so cut. Going into some more flex question or explanations, I'm going to use our laser pointer for here. So as we start at our water and slowly go up to our L2, so as we go from L1 slowly to L2, our concentration of water is decreasing. The higher and higher we get, or the further and further away we get from L2. L1. And same will be seen with our nitrogen here. As we start from L2 and get close to L1, our nitrogen concentration is getting lower and lower. And you think that would similarly happen with our nitrogen flux, but this isn't necessarily true. So next what we're going to do kinda is write out our flux equation. So we're going to have N1 is equal to J1 plus X1 times N. So our N1 is just going to be our overall flux of component 1. And then we have our J1 here, which we already defined as Fick's law, or our molar flux, which is what we're going to be solving for later. And then we're also here we got to add our X1 plus N. So N is going to be our overall flux of in this case component 1 and 2, but could be possibly more, I'm assuming, if you have a bigger system. And then our x1 is going to be equal to our molar fraction. So I'm just going to put mol frac. So that kind of explains our law we have going on here. So our n of n2 is going to be equal to 0 because it cannot break this level here. It cannot go any further than this H2O. So it kind of maxes out its potential there. So we can write n of our n2 is going to be equal to 0. Excuse me. And then so also n1 will be equal to n, since n1 plus n2 equals n. So now we can kind of plug in our equation a little bit. Well, we can plug in our equation. So we're gonna start with our nitrogen. So n2 is going to be equal to j n2 plus x1 plus n, and n is going to be n2 plus n h2o, which we already know. n2 is going to be equal to 0. We can just cancel this out. So rewritten, we're going to have 0 is equal to jn2 plus x1 h2o, nh2o. And we want to solve for jn2, so we can subtract it over, and then we want a positive jn2 just as an example. So there we go. So we're going to have, and for this specific case, here we're going to have our molar flux of nitrogen is equal to the negative mole fraction times the overall flux of water. So knowing these equations, we can start with question 2, which is for a typical gas phase diffusion coefficient of 10⁻⁵ meters squared per second, estimate the molar flux of water in a tube with a vapor length of 1 meter at 50 degrees Celsius and 1 bar of overall pressure. So I'm going to draw a diagram right down here, and I will be back. Okay, we're back for part 2. I have our diagram here drawn. So over here on our left, we have the same kind of cup, pool in this case, with water in the bottom, a mixture of water and gas and nitrogen at the top. Water and nitrogen gas, and nitrogen gas at the top. Our water level is equal to 0, and at the top of our pipe, I believe, which is what we're looking at, is 1 meter. And then this area, or this length, I guess, in between these two areas is going to be areas. I gotta stop saying area. In between these two lengths is dz. We have our temperature at being 50 Celsius or 323 Kelvin. We have our pressure at 1 bar, and we have our diffusion coefficient at 10⁻⁵ meters squared per second. 3 other things I just copied down from what we did up here in part 1 was our Fick's law. I have our total here equaling our sum of our 2 parts, and right here we just have what we did, our PV equals nRT adaptation to concentration. Now, since the question is asking for molar flux of water, we need to do everything in terms of water. So let's start with writing our balance down. So we're going to have our NH2O is going to be equal to J1 plus X1N. So JH2O plus XH2O So now what we need to do is just sub in our values, and we can start using these PV equals nRT terms. So we'll have NH2O is equal to, for J now, we're going to substitute in Fick's law here, kind of. Did we simplify Fick's law up here? Okay, no, I'll do it in this problem, but Fick's law here, I'm just going to plug in D, and then we'll have our negative C, but our negative C, I'm going to be using these PV equals nRT terms. And then we'll just multiply by our gradient here. We'll kind of rearrange this equation and do D times C times the gradient. So what we'll have is gotta make sure, we'll do the C first. So C is negative, so negative P, so this part. Let's give me more space. Negative P, and then times D, and then we gotta use the rest of our nRT, or our NT. And then we'll multiply by the gradient, which is going to be dxH2O over dz. And then plus the rest, which is xH2O, and then times N, which is going to be NH2O plus N2, which is 0. So we'll just have NH2O. Okay, looks pretty good right now. So we just got to start simplifying, and we'll integrate. We're going to rewrite it now to make it easier to integrate later, so we're going to get everything on respective sides. So first what we can do is we can move our xH2O, so let's do NH2O, because we want to integrate that side. 1 minus xH2O, which is going to be equal to our negative PD from 1 to 2. Yeah, over RT. Then we can kind of just multiply by dxH2O. Make sure you can see me. Okay. dxH2O over dz. I think that's it. That looks right, yeah. And then what we're going to want to do now is we're going to want dz on the left side. So let's get dz on the left side. Sorry, I had to think for a second there. So we're going to have NH2O times dz, because we can just multiply that over, right? Yeah, and then we'll divide by 1 over x. Yeah. Okay, that was easier than I thought. I don't know why I tripped up on myself. Because we can simply just swap these values. Sometimes this basic algebra gets me. Okay, that looks good. Now we can integrate, but we got to find a range first for the integrals. So let's do that now. Find a range. So we know our dz is going to be from 0 to 1, so we can just write that over here. I'll just write 0 to 1 like that. And then that's 4 dz. And then we need to find one for our dx, which we don't necessarily know yet. So we're going to have to solve for that. So we're going to have our x H2O, which is equal to our partial pressure of water over our total pressure. And I'm going to have to figure that out, so I'll be back. So after some Googling, I found that at 323 Kelvin, our partial pressure of water will be 12 times 10 to the third pascals. And then over our total pressure, we're going to divide by 1 bar. And we're going to get a ratio of 0.12. So that means we're going to integrate dx from 0 to 0.12. Okay, now knowing that we can start integrating. So we're going to integrate this left side. We're going to have NH2O. And then we're going to have our integral from 0 to 1 dz, but I'm not even going to write it because I already know that's just going to give us a 1. So I'm just not even going to write the integral. And then we're going to have is equal to our negative stuff outside of the integral we don't need to worry about over RT. And then we're going to integrate from 0.12 to 0 of 1 over 1 minus x H2O. Yep, okay. And then dz, or dx, sorry, H2O on our outside. So starting to look really good now. I'll be back in 1 second. So next let's add a page so we can just further simplify this integral. We're not going to do anything on the left just yet. So when we evaluate the integral of a fraction, we're going to get the natural log of absolute value, of x H2O minus 1 close value, and then that's going to be evaluated from that 0.12 to 0. And then so what we did here and then we can also get rid of, I believe we can get rid of this negative sign too with the integral. Okay, now all we have to do, I'm just going to rewrite everything. And then when we evaluate, looks like a D. When we evaluate, we're going to get the natural log of one over, I'll be back. We're going to get a value of 1 over 0.88. So all we have to do now is finally just plug in our pressure values, our coefficient values, and our constants in temperature. So, we're going to have our NH2O equal to, I have a big line. We're going to have our pressure, which is 1 times 10 to the 5th pascals, times our D, which is 10 to the 5th, negative 5th, that is, meters squared per second, I think, yeah. And then our R, which is a constant of 8.314 kilograms times meters cubed second squared times mole times K, and then multiplied by temperature, which is 323 Kelvin, right, yeah, and then times our natural log of 1 over 0.88, which is equal to 4.76 e negative 5, reported in units of mole meters squared second. So this will be our final answer. for the value we found to be the molar flux of water for these given values.